Okay, so today we're going to talk about the continuum hypothesis, or the idea of how do we describe the equations of motion that we want to use to describe how a fluid moves around. And we've already talked about the idea that one thing we want to do is we want to consider that that fluid is a continuous medium, or as a contraction, what we call a continuum. And so we had this idea that maybe we have a material point, and we might be interested in asking how is it moving through space as a function of position and time, but we have to recognize that in reality this material blob is made up of lots and lots of individual molecules. And we said that this little material volume, if we give it a volume, let's call it a differential volume dV, as we shrink it smaller and smaller and smaller, then we can treat the fluid as a continuous medium that's differentiable at every single point, so we can calculate things like the gradient of the velocity or something like that. But we have to recognize that as we make it smaller and smaller, maybe when we've got fewer and fewer molecules in there. So the question we really want to ask is if the fluid is a continuum, and we've taken no account of the molecular nature, how is this consistent? If got no account of the molecular nature, then how is it going to be consistent with the idea of describing this thing as a continuous medium? And really the key thing behind the continuum hypothesis is that we have to assume that even in this tiny little small volume that we have here, there's going to be sufficient molecules that when we measure the properties of any individual molecule, that when we take them all up and we average them all together, that we're going to get a well-defined average. So rather than saying the velocity, or maybe we could also be interested in, say, the density or the temperature or any other molecular property of this material. Let's do something generic. And so let's write as a generic property, let's define some property, we'll call it phi, and we're interested in its average over all of the molecules that are in that box. And so we're going to add up all of the properties of the individual molecules. From I goes from 1 to n, and then we'll take the average and we'll compute that average value. And so this value phi is just a general variable that could be any property of the material. And what we have to do is we have to make sure that we're averaging over enough property or enough individual molecules that we get a well-defined average. So to try and quantify this, let's imagine that we take a little box of material. And let's say that you have a sensor in the lab that's a very, very sensitive sensor, and maybe the size of the sensor is about 1 micron on a side. So the volume of your sensor is it's really averaging the properties that's on the size of 10 to the minus 6 meters, but then cubed. So the volume of the box that you're averaging over is something like about 10 to the minus 18 meters cubed. And you're going to measure the average properties of a material in that. And then we're going to plot that average. Then what about if I give you a bigger sensor that's, say, 10 microns or 100 microns or 1,000 microns? What do we get in terms of an average? And then we'll plot that information, and we'll make a plot of it on a logarithmic scale. So on this size, we'll put the log of the characteristic size of our box, L, and so that would be something like the volume to the 1/3 power. And so the particular example that I wrote here was maybe where L was 10 to the minus 6, but it could be bigger, and it could be bigger and bigger and bigger and bigger. And then we'll plot the property, this average property. And the key idea behind the continuum hypothesis is that we find that there's a wide range of regions over which we do indeed get a well-defined average value. Now, if you make this box smaller and smaller and smaller, if you shrink it, eventually you'll start to find that you start to see fluctuations. So you'll start to see that you get fluctuations in your value. And typically that happens down below sizes of somewhere around about a micron. So, for example, this is the region where Brownian motion plays a role. So Brownian motion becomes important. And where specific size fluctuations become important. So in a solid, for example, let's say you're measuring the average density of, let's say, a piece of carbon, this would be where you would find that buckyballs and carbon nanotubes and other things have very large nanoscale fluctuations. So these would be nanoscale fluctuations. And of course, there's money to be made down there if you find materials that have, for example, much better properties or much lower properties, lower densities or higher densities than the average value. But for the rest of this course, we're going to be interested in the idea that this average property that we measure is going to have a well-defined average over a wide range of scales. Now, if you make the scale size even bigger and bigger, eventually you'll start to see system size dependence. And so eventually you'll find that this starts to change. Now, I've drawn it as decreasing. Depending on the property, it may increase. As a good example, think about calculating the density or measuring the density. If you make your box size bigger and bigger and bigger, eventually your box is so big that the density in the upper atmosphere is lower than the density in the near ground level. And so this is where you'd start to see system size dependencies. And frequently this might happen beyond scales of, say, somewhere round about, who knows, between 1 to 1,000 meters, depending on the property of interest. But this gives us a very, very wide range of scales over which a continuous medium approximation is going to be a good example. Now, if you don't believe me, then we can do a couple of examples. So let's think about working out a couple of specific examples. Let's first of all think about taking an example of air at standard temperature and pressure. So imagine a little box of air at standard temperature, which is 298 Kelvin, and a pressure of 1 atmosphere, or 10 to the 5 newtons per square meter. The question to ask is how many molecules are in a little box of size dV, which is 10 to the minus 18 meters cubed. And to evaluate that, we need something that relates pressure and temperature and volume, and that's, of course, the equation of state for an ideal gas, which we can write in a simple way as P times the volume is the number of molecules times nRT, where R is the ideal gas constant, which hopefully everyone remembers, or you can look up, and is 8.314 joules per mole per Kelvin. So if we take all this information together, I can rearrange this, and I can find that indeed N is nothing but the pressure times our volume, which is dV, divided by R bar times T. And if you put all of these numbers in and evaluate it, then you'll get a value that comes out to be something like about 2.4 times 10 to the 7 molecules. So this average that we're calculating is not an average over 10 or 20 or 100, but over 20 million molecules, and that's why we get a very, very well-defined average value. We could do a second example. We could think about, what about a little micron cubed of water at standard temperature and pressure? And again, we might like to calculate how many molecules we would be averaging over. Now, this time we clearly can't use the ideal gas equation of state. That's not appropriate. But we can understand the idea that the density of water is about constant, and the density of water is 1,000 kilograms per meter cubed. So that's a good value for the density. We need to go from the density to thinking about how many molecules there are. And so the only other piece of information we need is we need to know the molecular mass of water, which is H2O, which is two hydrogens and an oxygen. And so that's 18 kilograms per kilomole. And then we need to remember how many molecules are in a mole, and that's Avogadro's number, which is 6.02 times 10 to the 3 molecules per mole. So if we take all this information, we can put that together as well, and you can work out what the number is. And the number turns out to be, if you work this out, you'll find that you get a number something like about 3.3 times 10 to the 10 molecules. To do that, just remember you have to be a little bit careful about moles and kilomoles because there's an extra factor of 1,000 there. But so within one tiny little micron cubed of water, you're really averaging over something like 10 to the 10 molecules. And so from now on, we will think that we don't have to think about the idea that there's lots and lots of molecules in there. We're just going to replace this by a continuous medium, which is going to be able to be described as having a velocity and a density and a pressure and a temperature that are all just continuous field variables that we can then differentiate.